In this video, I'm going to quickly go through the concept of Hamiltonian for an atom. In this case, for example, I want to talk about the Hamiltonian for helium, because that is the simplest system after hydrogen, right? After hydrogen, it is helium. So in this case, we have the Hamiltonian for atoms. In this case, is our equation here. So remember what the Hamiltonian represent. The Hamiltonian represent the total energy of the system. And when you talk about the total energy system, you have to consider the in the case of an atom, you have to consider the kinetic energy of each individual electron, which is what this part is responsible for. If you did any quantum mechanics course, you should recognize this, right? And then the second part, which is responsible for the potential energy of each individual electron. So kinetic energy, potential energy. And then you have the last part. So the last part is responsible for the mutual repulsion between electrons, because they're both negatively charged. So this is repulsion between electrons. And these are all the factors that contribute to the total energy of the system. So in the case of hydrogen, right, you wouldn't need to consider this latter term because you only have one electron, right? So there's no mutual repulsion between electrons because you only have one electron in this case. So this equation describes the Hamiltonian for an atom, and this equation is very hard to solve. And then for any atom that's bigger and that has more electrons than hydrogen, there is no exact solution to it. So meaning that for the Hamiltonian for all the atoms, only hydrogen has the exact analytical solution. Whereas the other case where you have multiple electrons, which we're gonna talk about it just in a bit using the example of helium, there is no exact analytical solution. So now we have the Hamiltonian for an atom. Then, for example, if we want to write down a Hamiltonian for helium, right? So what would you do? So helium. So first of all, what do you have in a helium? You have the nucleus, you have the two electrons, right? So in this case, compared to hydrogen, which is one electron, you have two electrons. So two electrons, so in the total system, there are two electrons. Then you will need to consider the kinetic energy for both electrons and the potential energy for both electrons. And now we have to introduce this mutual repulsion between these two electrons. So for helium, the Hamiltonian is going to be so you have the first kinetic term and the first potential term. So this whole thing represents the kinetic plus potential for electron 1, right? And then we need to look at the other electron, because each individual electron has their own kinetic energy and potential energy. So the second one will be the same equation, but we're gonna have 2 for our Laplacian operator here, and -1 for pi 2e squared r2 rather than r1, because we're looking at the second electron, right? So this is ke plus pe for electron 2. And I'm just gonna shrink my writing a little bit because it's not fitting right now. So let's just shrink this a little bit. And then we write down a mutual term, which is plus 1 over 4 pi e squared r1 minus r2. If you observe this equation, you might notice that in this equation, you don't have the 1 over 2 in front of the thing. So the reason why is because the 1 over 2 is here to account for something so-called double counting. So if you're familiar with this summation, you'll know that double counting occurs when you include the same interaction multiple times. I'm thinking of an example to explain this. Okay, so if you want to look at a system of 3 particles, the interaction would be, let's say, 3 particles, right? It would be E is equal to V R1 minus R2 plus V R1 minus R3 plus V R2 minus R3. So if you blindly sum over all pair, like if you write this in terms of sum, you're gonna end up with this. If you write it like this, for this expression that we have here, and you expand this, you'll actually get 6 terms rather than 3 terms, which is what we do not want. So hence, to avoid counting the same terms twice, to make it like unique, we need to divide the summation by half. But in this case of helium, so let's get back to our topic. So in this case, when we have helium, since there is only 2 electrons, R1 and R2, so there's only one unique electron-electron interaction, so there is no double counting. So therefore, we don't have the 1/2 factor in front of it, but everything else should be the same. And the helium atom has 2 electrons. So in an excited state, 1 electron remains in the hydronic ground state, which we denote as psi 100. And the other one is promoted to a higher energy state, so psi NLM. And if both electrons are excited, what happens is that their energy can surpass the ionization limits, causing 1 electron to escape, so leaving behind a He plus iron and a free electron, right? That's weakened. So that's what happens if both electrons are excited for helium. And something very important also about helium is that if you remember, the total wave function for 2 electrons or 2 identical fermions must be anti-symmetrical. If you have no idea what I'm talking about, I'm suggesting you to go check out the videos I have done earlier that I talk about identical particles, and I explain what is anti-symmetrical and what is symmetrical. So according to the Pauli exclusion principle, the total wave function of identical fermions, in this case 2 electrons, must be anti-symmetrical on the particle exchange. So the total wave function for our helium total is going to consist of the spatial part and the spin part. And in my previous video, I have mentioned that for your total wave function to be anti-symmetrical, your spatial and your spin part of the wave function must be, like, if the spatial part is symmetrical, the spin part must be anti-symmetrical, and vice versa. If the spin part is symmetrical, then the spatial part must be anti-symmetrical. So I mentioned the reasoning for that in my previous video. If you don't know this, you can also go check that out. But anyway, the takeaway is for a pair of identical fermions, so which we have here 2 electrons, the total wave function here must be anti-symmetrical. And the result of that is that our spatial is symmetrical, or that it is anti-symmetrical, and our spin has to be opposite of whatever our spatial is, and vice versa. So there are 2 cases we can consider, which is the first case, what we call a perihelium. So what is a perihelium? Perihelium is when the spin part is anti-symmetrical. So remember when the spin part is anti-symmetrical, it's in a so-called singular state, right? Singular configuration, I think. Singular configuration, and then for symmetrical, it will be a triplet. So in this case, if our spin part of the total wave function is anti-symmetrical, what is our spatial part symmetrical or anti-symmetrical? Our spatial part is going to be symmetrical, right? Because remember, if the spin part is anti-symmetrical, the spatial part must be symmetrical because it has to be whatever the opposite of what your spin is in order for the total wave function to be anti-symmetrical. So in this case, if our spatial function is symmetrical, the result of that is that the electrons in this case are closer together in space because their spatial wave function are symmetrical. So this leads, so if they're closer, this leads to a higher electron repulsion and thus higher energy, right? Because when these electrons are closer together, the repulsion between them gets higher and thus leads to an overall higher energy in the total system. And now here's the second case, which we call orthohelium, which is, you can guess it now, when spin is symmetrical. And it's called a triplet configuration. And in this case, if our spin is symmetrical, is our spatial function symmetrical or anti-symmetrical? Our wave function is going to be anti-symmetrical, right? Because I repeated it multiple times, it has to be opposite of whatever you're choosing. So anyway, if our spatial part of wave function is anti-symmetrical, that means the electrons are further away from each other. So they're farther apart in space because of the anti-symmetrical spatial wave function. So that is going to result in a lower repulsion rather than a higher repulsion. So thus in a lower energy. So overall, when you compare a perihelium to an orthohelium, you see that for a perihelium, it generally has a higher energy overall because the electrons are closer together, and there's a stronger sort of repulsion between them. Whereas in the orthohelium place, the repulsion is less and thus lower energy. So that's something about helium that you should know. And in my next video, I'm going to talk about the periodic table. So thank you guys for listening. If you guys have any questions, feel free to comment down.